The toughest search and rescue boat ever built takes on any weather, anytime. Virtually unsinkable. Jet engines get planes airborne and keep passengers comfortable at high altitudes by driving vital cabin pressure and the vacuum toilet. This is the power split device in a production hybrid vehicle. Before it was pioneered, cars like this still lived on the drawing board. The redesigned Zeppelin is making a comeback. It looks retro, but this is no history project. Let's take a look inside these machines and see how they work. This is a motor lifeboat, or MLB, a first response search and rescue vessel used by U.S. and Canadian Coast Guards. One of the toughest marine machines in the world, the MLB saves lives in near impossible conditions. It's a 14-meter powerhouse that takes on hurricanes, heavy seas, surf, and winds up to 110 kilometers an hour. And if the boat capsizes, it pops back up again in seconds. It's basically unsinkable. Let's take a closer look. The MLB has a cruising range of about 370 kilometers, a top speed of 45 kilometers an hour, and can tow a vessel 5 times its weight. It's got 4 crew members: the pilot, engineer, and 2 hands, with room for 5 passengers. Its hull is made from marine-grade aluminum that won't rust, is as strong as steel, but a lot lighter. So the MLB can take a 6-meter drop from a wave and slam onto the surface without a dent. But for this boat to save lives, it needs to go fast, so its hull has been molded into a very special shape. To get up to speed, you need a knife-like hull to slice through rough seas and a flat hull to ride high on top of waves. So this machine has what's called a deep V-planing hull, sharp at the front, flatter at the back. Next up, a big power plant and some fighter jet steering to move it through the water. 2 435 horsepower diesel engines drive stainless steel shafts attached to props that need constant maintenance. If these snap off, the rescue's over. The boat's 4 operator stations are controlled from either the enclosed bridge or outside on what's called a flying deck. For maximum control, the MLB uses a fly-by-wire steering system that responds directly to manual inputs and allows for rapid response with little effort. A turn of the wheel is converted to electronic signals that a computer translates into instructions for the boat's rudders. These systems are ideal for machines that work in brutal conditions and have been standard equipment on fighter jets for decades. And like some jets, the MLB can fly upside down. Well, maybe not fly, but it can recover from a flip with the ability to self-right. Thanks to its low center of gravity, the MLB can hold its course at almost 90 degrees. But it can flip. And when it does, there's enough buoyancy in these 5 watertight chambers to right the ship, even if 2 of them get swamped. That's because of the boat's ballast ratio. Basically, air bubbles trapped at the bottom want to rise to the top. The engine's weight and location also help the rolling motion. And there's one more flotation chamber up here, for good measure. Nothing's left to chance. And that's a good thing for crews when an emergency call comes in from the unpredictable Pacific Northwest. Finding victims can be as much of a challenge as getting to them. A spinning direction finder scans for distress beacons. The signal hits the finder's two sensors at slightly different times. The radio direction locator uses this data to plot out where the distress signal is coming from and keep the MLB on target, even if thrown off course by rough seas. On a clear day, finding the victim starts up here on the flying deck. Just an extra 2 meters height buys you a full 4 kilometers of sight. The flying deck's point of view also makes things safer during close recovery of folks in the water. And recessed wells, cut just a few centimeters above sea level, make it easier to pick up waterlogged victims. The MLB's survivor compartment, located in the center of the vessel, helps keep victims stable. It's watertight and climate-controlled to help survivors who may have been injured or submerged in icy waters. There's one other spot that has the potential to flood this ship. Its windows. The enclosed bridge is there to provide a safe, watertight compartment if the crew needs it. But after some extreme testing, it turned out that screw holes in the frame, not the glass, weakened the windows. So they ended up sandwiching acrylic sheets between the aluminum frames beyond the window's edges, spreading the force of the waves over a larger area. The MLB, a powerful machine that's almost indestructible, custom built for the survival of victims and for the safety of its crews. When you're stuck in a plane at 35,000 feet, there are a few things to be thankful for. Jet engines, air pressure, and the vacuum toilet. Jet engines keep us safe and sound, and not just by keeping the plane in the air. They help maintain cabin pressure, and that keeps the toilets working. Let's see how it all works. Jet aircraft use gas turbine engines to get off the ground. A turbofan sucks in air that gets compressed, burnt up in a combustion chamber, and then spins a turbine. The burning jet fuel mixes with oxygen to produce pressurized gas. That's what spins the turbines. And they generate energy in the form of jet exhaust. That has enough thrust to propel the airplane forward, get it safely airborne, and keep it there. But that's just one way the engines play a role during flight. Commercial jets fly at high altitudes because the air is thinner, and that means they get much better fuel efficiency. Good for jets, bad for people. The thin air means less pressure and a lot less oxygen. So, how do the engines help? Each engine sucks in over 1,000 kilos of air per second to propel the plane forward. 20% of that air is captured and redirected into the plane. But you can't just go blowing that into the cabin. At this point, it's hot enough to roast a chicken. So, rams on the plane's belly take in the ice-cold, high-altitude air. The two streams are mixed, temperature is adjusted, and then it's forced into the cabin to create pressure. A butterfly valve regulates the amount of pressure inside the plane. If it gets too high, the valve releases air automatically. And despite what movies tell you, these doors cannot be opened when you're high in the sky. Air pressure locks them in place once these edges seal the door to the inside of the fuselage. At 35,000 feet, with cabin pressure 4 times higher than what's outside, passengers are kept alive and comfortable. But not that comfortable, unless this is working. Imagine crossing the Atlantic without one. So what's the engine got to do with that? First, here's a gravity toilet found in your home. When it's flushed, water from the tank fills the bowl. It moves into the U of the mechanism. This creates a siphon that pulls everything down the drain. A water and gravity flushing system's not an option on an airplane. Too big, too heavy, uses too much water. So engineers turn to vacuums to solve the problem. And this is where the jet engine and the cabin pressure it produces comes in. When you flush a toilet on an airplane, there's a loud rush of air. And as long as you hold down the button, it keeps on sucking. That's why the airplane toilet is called an active vacuum system. High-pressure air in the cabin is always looking to escape to the low-pressure air outside the plane. So it's harnessed with every flush. Flushing opens a valve that sucks high-pressure air from the cabin with waste material into a septic tank. The tank lives in the unpressurized belly of the plane. A vacuum is created by the difference in pressure between the toilet and the valve. The septic tanks are emptied when the planes are back on the ground. Despite a few myths out there, waste doesn't get launched into the blue. The only thing coming out of here is air. And despite all that pressure sucking the inside of the bowl, there's no chance of getting stuck on the rim if you flush while sitting down. The seat design allows air to circulate through these openings and prevent a seal from forming. The vacuum toilet is highly efficient, just 1 liter per flush on some models. Our toilets at home use up to 6 liters for each one. And if you've ever been stuck on the tarmac for a couple of hours, you'll appreciate this little add-on device. It's called a vacuum generator. On the ground, the air pressure inside and outside the plane is identical. There's no natural vacuum. That doesn't kick in until the plane passes the 16,000-foot mark. No bigger than a 2-liter bottle, this generator is a powerful version of a home vacuum. Using a fan, it sucks air from one end and blows it out the other, keeping the call of nature at bay until air pressure kicks in. The jet engine spawned a travel revolution, allowing us to fly around the world non-stop for up to 18 hours while keeping us breathing and comfortable. This is a gas-electric hybrid car. The idea behind this machine is to increase fuel mileage and reduce emissions of a gas-powered car while overcoming the long-distance limitations of an electric car. Looks like a regular ride, but peek inside and you'll find new parts and innovations that made the whole idea possible. Let's see how it works. When it comes to vehicles, hybrid simply means using 2 or more distinct power sources to create motion. There are lots of different types of automotive hybrids out there, but the most common ones are called parallel hybrids. That's where the 2 power sources work alone or together, side by side, or parallel to each other. The big challenge for engineers? Produce a gas miser that gets to highway speed as fast as any big guzzler, with only a tiny engine, an electric motor, and a big set of batteries to turn the wheels. But to do that, engineers had to figure out how to get the gas and electric motors to work together to maximize fuel efficiency. Then, keep the batteries charged so you never have to plug them in. It takes about 200 kilograms of batteries to store as much energy as 1 liter of gasoline. So, until the technology radically improves, we're going to be using some form of fuel-powered engines in our cars. There are 2 things that dogged hybrid car makers when it came to balancing fuel economy with performance. A small gas engine is really efficient when cruising at a fixed speed, but it lacks kick on acceleration. An electric motor gives instant pickup off the mark, but dies soon after. Hybrid makers wanted both, so they dreamt up a clever device that makes the electric motor, gas engine, and battery charger talk to each other. It's called a power split device, the real brains behind this pioneering hybrid. A set of gears drive a chain that's connected to the axle that drives the car's wheels. It's the delicate interplay between the gears that determines how much fuel you burn. When you first start rolling, the electric motor spins this outer gear. And that gets you up to speed without wasting a drop of gas. Perfect for the stop and start of day-to-day driving. But you wouldn't want to hit the highway on batteries alone. Electric cars only go a couple hundred kilometers before they need a recharge. So once you get up to speed, the gas engine kicks in. It all happens through the power splitter. These 4 planetary gears start to spin, boosting the car's power. This center gear also goes into action. It's connected to a generator that either charges the batteries or sends extra power to the electric motor. It's so smooth, the driver doesn't feel a thing. The only sign of change is on the monitor that lets you know which power source is working. You're now burning gas at peak efficiency and charging the batteries, never having to compromise power. When it's time to pass a slowpoke, the electric motor has enough juice to fire up again and add power to the gas engine. So even when you hit the gas, you don't waste any. The hybrid's computer keeps track of power consumption and sends ongoing commands to the power splitter. It stops the gas engine when you don't need it and starts it again when you do. It even kicks it into a battery charging idle if it senses your system is getting dangerously low. The electric hybrid's power split device opened the floodgates on innovation. This machine marks a turning point in automotive engineering that's giving drivers what they want. A powerful yet low-cost ride that goes a long way. This is the Zeppelin NT, an airship whose roots go back to the 1890s. The old-style Zeppelin is infamous for this, but that's ancient history. New high-strength fabrics, lightweight aircraft composite materials, and computer-guided systems have revolutionized the airship. Longer than a 747, but a fraction of its weight, the Zeppelin is back, hoping for a future moving people and cargo. And that's not hot air. The helium-filled NT stands for New Technology, vectored props, digital joysticks, and 3 aircraft engines. This machine cracks highway speeds while cruising at altitudes above 8,000 feet. And it can stay in the air twice as long as a commercial airliner. Let's see how it works. The NT gets its lift from helium gas. Older generation airships were filled with much cheaper hydrogen, but they were a little volatile. Modern Zeppelins use helium, a noble or non-reactive gas, highly stable, almost as buoyant as hydrogen, but very expensive. That's why the NT's outer skin is made to prevent leakage. And that's tricky, because helium molecules are extremely small. A party balloon loses its lift over time because the helium literally escapes through the skin. Airships need a much tighter helium barrier. So the NT is clad with a material woven tight enough to contain most of the helium. And this machine needs a lot of it. In order to go up, it has to hold enough gas to help its engines overcome gravity. About 1 cubic meter of helium gives you 1 kilogram of lift. The NT holds about 8,000 cubic meters of helium, so it should be limited to lifting about the same weight. But it can lift close to 10,000. How does that work? The NT is technically not lighter than air. So unlike its predecessors that always wanted to float away, the NT can be made to sink. This makes loading and unloading people a lot simpler. But how do you fly a floating machine that's heavier than air? To rise up, the NT needs thrust and power from 3 200-horsepower engines. 2 are mounted on the side of the hull. The third is mounted at the rear. They power variable pitch propellers. Rotate them up, hit the gas, and away you go. The rear engine also controls a second fixed propeller that helps move the machine from side to side. During boarding, the airship is in control, held in place by the engines while passengers get on and off. And its final takeoff mass is adjusted by a water ballast system that can add or take off weight depending on how many passengers have climbed aboard. Once airborne, the propellers rotate again to provide thrust and propel the airship forward. The 3 engines give the ship a tight turning radius, with a computer-controlled steering system wired to the pilot's joystick. And that means instant response to changing conditions, maneuvering like a helicopter, hovering, moving sideways, or turning on a dime. But this isn't just a motorized airbag. A highly engineered skeleton holds it all together. The Zeppelin's gondola, rudders, fins, and stabilizers are all mounted to triangular graphite frames. Aluminum girders connect them along the length of the ship, and it's all held together by super strong cables. The NT's internal structure allows for bigger engines and bigger loads. There is one problem the Zeppelin has to solve in managing its helium. As you rise in the atmosphere, air gets thinner and helium expands. The opposite happens as you descend. Air expands and helium contracts. Both situations affect your ability to stay airborne. So the NT uses air-filled ballonets to keep air and helium balanced. They maintain the hull's perfect shape by increasing or decreasing the amount of air pressure inside it. The ballonets release air as the airship rises and pump outside air in as the machine comes down. That takes care of flying. So how do you land this thing? Because the NT is heavier than air, the pilot just has to ease off the engines and change the pitch on the props to gently set her down. Once landed, the airship is locked onto a 20-ton mobile hydraulic mast. Even in high winds, the mast allows the ship to turn a full 360. The newly minted Zeppelin won't set any airspeed records, and you may opt for an airplane for rush delivery. But for cheap, efficient lifting and a fun way to fly, the NT may have found its niche. A massive city on a deadly floodplain. London's Thames Barrier holds the line against powerful storm tides. It's the most powerful and durable locomotive working today. The diesel-electric is a workhorse and power plant all in one. Ever wonder what's going on under your feet when you're pumping gas? Inside the self-serve gas pump. Win, place, or show. When it's nose-to-nose and stakes are high, all bets are on the photo finish camera. Let's take the lid off these machines and see how they work. This is the Thames Water Barrier, the single most important flood defense system in the world. There are other barriers, But none come close to this machine's burden of protecting over 1 million people and billions in real estate. Its job is simple: stop a river from putting London underwater. Let's see how it works. Stretch a set of gates 520 meters across the River Thames to block it. Now, do it in just minutes as thousands of tons of water rush towards you. Then, when the threat's over, retract the gates quickly to let boat traffic through. And keep it working for decades without ever breaking down. The barrier was first used in 1983 to halt a storm surge from the North Sea. Surges that slam into the mouth of the Thames are a huge threat to London. Combine a storm with the river's high tides, and you've got a major disaster. Big parts of London would be swamped by floodwaters. So, to protect people and the city, engineers had to figure out how to block the Thames while maintaining its shipping channels. Their first big challenge was location. They chose a spot 15 kilometers from the Houses of Parliament, where the banks are straight and the riverbed sturdy enough for a massive concrete foundation. There are 10 gates in total that span the Thames. 6 sector gates that rise from the river. These include 4 large central gates and 2 outer ones. There are 4 smaller gates by the riverbanks that live above the water unless they're in use. All of the gates are hollow and made of steel. They fill with water when submerged and empty when rising from the river. Each of the 4 large gates is a hefty 3,300 tons, almost half the weight of the Eiffel Tower. The next challenge was how to get the gates out of the way quickly and safely. These radial arms drive the sector gates under the water to lie flat in concrete sills on the riverbed. This allows the free passage of river traffic. If forecasters spot a threatening storm, they notify the Port of London so that shipping in the area can be given the heads up. Red X's on the barrier tell ships to stay put. Operators in this tower control the movement of the gates. The closing sequence is designed to work with the natural flow of the river. After the outer gates are dropped, the sector gates are raised in pairs from the outside in. If the command center's computers were to crash mid-emergency, each pier has its own set of independent controls. And if they fail, the rams can be manually cranked. With millions of people and billions in property behind this barrier, nothing's left to chance. Even these radial arms are doubled up. Each one is powerful enough to move a gate on its own if the other arm breaks. They're powered by sets of hydraulic pistons. The top arm pulls in, while the bottom one pushes out. This rotates the sector gates up and into a defensive position. Operators normally close the barrier in about 90 minutes. In an extreme emergency, the entire thing can be set in place in just 15. But if you shut it all at once, the force of the entire river hits the barrier at the same time. And that could send a deadly rebound wave back downriver. If floodwaters ever threaten to top the gates, they're raised a little more to allow a controlled amount of water through. This is called an underspill position. It kind of acts like a dam controlling the levels of a reservoir. The closest any flood has come to topping the barrier is 2 meters. So far, so good. The entire operation is electric and has 3 independent sources of power. Electricity from the grid flows through cables in tunnels beneath the river. If the tunnels flood or power gets cut, there are 3 backup generators, each powerful enough to operate the entire barrier. The electrical bill for one turn of these screws? Almost 6,000 euros. On to the final challenge. The gates need constant maintenance to fight rust and water damage. How do you get that done without shutting down? By designing the whole thing for high and dry repairs. The gates come with an extra hydraulic piston to rotate them up and out of the water, so workers can repair damage and touch up the paint job. The gates do spend most of their time underwater, so paint is needed to fight rust. It takes about 40 tons of paint, figure 10,000 cans, just to cover one of the 4 large gates. The barrier has averaged about 5 closures per year since it opened. But if forecasters are right, there could be as many as 30 per year in the coming decades. And that's quite simply because water levels have been rising steadily. Only time will tell how long this astounding work of engineering will hold up. It's among the most powerful, most durable train engines working today. The diesel-electric locomotive is a workhorse and power plant all in one. It can haul thousands of tons of cars at speeds of up to 200 kilometers an hour. And it can work on almost any type of track because it produces its own power. The word locomotive means self-propelled vehicle. And its challenges have always been the same. Create enough power to move cargo and people, haul them quickly and efficiently over distance, then stop them smoothly and safely. Let's see how it works. Straight electric locomotives need power from the grid to move. To keep them in business, you need expensive and hard-to-maintain overhead wires or electrified rails. But not all rail lines are connected to the grid. And if you're rolling on them, you need a diesel-electric locomotive, like this one. Producing power is straightforward on this machine. A diesel engine spins a generator that produces electricity. The electricity flows to traction motors on each of the axles. And they spin the wheels. You'd think it would be easier to get the engine to directly spin the wheels, like in a car. But then you'd need a massive transmission to handle different torques, speeds, and loads. The transmission would have so many gears, you'd need another train car just to carry them. Electric motors don't need transmissions. Increase the flow of electricity, and you increase their speed and power. Simple as that. A 16-valve diesel engine that puts out about 3,000 horsepower, spins a generator that produces over 2 megawatts of electricity, enough to keep 500 homes lit up year-round. That's a lot of juice, and it all goes to the traction motors located on each axle. This locomotive weighs in at 80 tons and has enough power to move over 30 times that amount. That's a lot of weight riding on the rails. So these machines rely on steel wheels to stay online. Other materials, like rubber, would warp and burn a lot of the locomotive's energy just to overcome friction. But this material has some problems of its own. Steel on steel is very slippery. And when shaped like this, all that weight can balance on the surface area of a dime. This helps with efficiency, but it sure causes problems with traction. Going around corners isn't an issue because the wheels have flanges to keep them on the track. But what about accelerating? To get started, engineers blow sand onto the tracks to give the machine all the grip it needs. The real work for this machine is managing all that weight when it's moving. To stop an object in motion, you have to convert all its kinetic energy into something else, like heat. A speeding bullet has way too much energy for glass to stop it. But thick steel is able to convert the bullet's energy into enough heat to melt it. Try stopping a locomotive pulling a full load of cars traveling at 200 kilometers an hour. Its kinetic energy is equivalent to 1,000 kilograms of TNT. Which is why fully loaded trains need about 2 kilometers to stop. When it's time to slow down, power to the motors is cut off. The wheels are now spinning the electric motors. This bleeds energy from the wheels, and they slow down. It's called dynamic braking. Most of the kinetic energy from the wheels is converted into heat that's dissipated through onboard resistors. Air-powered disc brakes also help out. Their spring-loaded pads are held open by air pressure. When you activate the brakes, the air pressure escapes and the pads close on the disc. And there's always sand available if they need more traction. What happens if the engineer falls asleep? This thing's basically a bomb on wheels. Which is why most locomotives come with a dead man switch. Unless the guy driving this thing hits this button every 30 seconds, an alarm sounds, and the machine automatically shuts down. The locomotive has been a giant in the transportation business for almost 2 centuries. Pound for pound, it's still the most efficient way to move goods and people over land. And thanks to the latest innovations, it shows no signs of giving up its crown. Gas stations pump out billions of liters of gas every day around the world. At one time, gas station employees had to do the pumping for us. And it's thanks to this vending machine that we now get to do it by ourselves. The self-serve fuel dispenser is like a robotic bartender. It measures, mixes, pours, calculates, and then gives us the bill. And because we're the ones handling a hazardous cocktail, this machine also makes sure we do it safely. Here's how it works. When we squeeze the handle and pour, 3 questions. How is the accounting done? What makes it stop when our tank is full? And if there's a spark, what prevents the tank and us from going up in flames? Gas pumps can deliver the goods in multiple grades, but they usually offer 3: regular, mid-grade, and high octane. The fuel comes from subterranean tanks that can hold up to 50,000 liters each. Most stations have 2. One stores regular, the other high octane. So where do the other grades come from? Simple. The system just mixes fuel from the 2 tanks and delivers exactly what you order. No matter what button you push, this little device gets it to your car. A submersible pump draws in the liquid gas and sends it out through a hose that connects to the nozzle. As soon as that happens, the counting begins. Along its path, the fuel fills a flow meter, a metal chamber that contains a rotor. It's called a pulsar, and it measures 1 liter of gas every 4 turns. An onboard calculator multiplies that number by the gas price and displays your running total. But there are problems with measuring gasoline and getting your money's worth when the temperature outside rises or falls. The density of gas shifts 1% for every 10 degrees of outside temperature change. If it heats up, gas expands. Cools down, it contracts. So if the temperature goes up during the day, you're going to get less gas on the drive home. Fortunately, these probes keep track of changes in temperature and regulate the flow of gas according to where the mercury is at. Meanwhile, we're squeezing the nozzle for all it's worth to get this over with. How does the pump know when to shut itself off? The gas pump comes with an auto cutoff system. It's a small tube that runs from the outside tip of the nozzle up to a sensor inside the handle. As your tank fills up, the nozzle becomes submerged. This chokes off the air pressure that was holding the handle open and shuts down the flow of gas with a familiar click. This is what protects us from getting splashed with liquid fuel. But how does it protect us from the explosive gasoline vapors that are released during pumping? A small motor is used to create a vacuum that sucks excess vapor from the nozzle. But the machine can't capture all the vapor, and that means there's always potential for danger. When sliding in and out of your car, you can create static electricity. If that hits the vapor, watch out. It's no urban myth. It happens. Luckily, gas vapor needs oxygen to burn. That means the flames could never reach the oxygen-free fuel tanks. Not enough O2? No explosion. Same goes for inside your tank. And when you get back in the car and turn the keys, you'll see this. That's because a styrofoam float has made it to the top of the tank, pushing up a metal rod that sends an electric signal to the fuel gauge, signaling that it's full. So the next time you're filling up, relax. There's a lot going on under your feet and in the box beside you to make sure the only bad thing about the experience is how much it costs. This is a digital photo finish camera, found at the end of every major race. It's a machine that can help make you a fortune or break your heart and bank account. Whether it's pointed at men, machines, or animals, there's no arguing with its results. Even if these photos look nothing like an average snapshot. Let's see how it works. Photo finish cameras do 3 things that normal cameras can't. Fit the end of an entire race into one frame, capture the exact moment each one crosses the line, and get a clear shot of all the competitors, even if one blocks another from view. But the photo finish camera doesn't just hang around waiting for the finish. An internal stopwatch is triggered inside the camera at the beginning of every race. And measuring them isn't just about the finish line. For results to count, competitors have to start on an even foot. At a horse race, the photo finish camera needs a starting gate. After the horses are loaded in, spring-loaded gates are shut and locked in place by these arms that are connected to a magnetic roll bar. When the starter hits the button, the magnet turns off, the bars release, and the gates fire open. And this machine stands by, ready to fire. It's an ultra-precise, ultra-sharp camera that costs about 8,000 euros. But you wouldn't want to use it for your vacation pics. It takes images that are just a few pixels wide, the perfect width to capture the finish. Just before the horses hit the line, The operator presses a button, and the camera starts firing at up to 3,000 frames per second. Each line image gets fed to a central computer, which arranges them side by side. Add it all up, you get this, the ultimate collage. That contains as many as 50,000 photographs. So while a normal snapshot shows one moment in time, a photo finish actually shows one location spread over many moments in time. Its high perch gives the camera an excellent angle on the proceedings. But there's always a chance of this: two bodies floating in the same digital space and time. So the camera uses a trackside mirror to produce a reverse angle. This captures all the horses, no matter where they are. Nothing escapes its digital eye. Once the last horse crosses the line, the operator edits out gaps so all the competitors fit on one screen. This image may be all gamblers and fans care about, but this machine knows a world record could also be on the line. As the photos come in, each one is tagged with a time, more accurate than 1,000th of a second. Line up the cursor with any competitor, and it tells you the exact moment they cross the line. This is what announcers mean when they say they're waiting for an official time. Totally unbiased, never blinks an eye, and it always tells the truth. One line at a time. The power of this all-terrain vehicle's engine can pop the wheels right off. But the Thundercat is built for takeoffs and hard landings. Soak, wash, and dry. This new style car wash babies your ride and your paint job on less than 10 liters of water. Most of us have seen elevators free fall in the movies. But what if the cable snapped on the one you're riding? The ATM checks your ID, calls your bank, and hands over the cash. Let's take the lid off these machines and see how they work. What keeps all-terrain vehicles, or ATVs, really popular is the way they power through axle-busting trails in one piece. How do you prevent the machine from flipping, falling apart, or flying off the trail? By matching its engine's power with the durability of its components, like the axle, suspension, and tires. This Thundercat H2 looks and sounds like every other ATV out there. But it's pushing the limits with one of the most powerful engines on any production ATV ever built. And to keep the machine from breaking apart under its own power, Thundercat designers had to rethink every other component and how the engine sends power to the wheels. Let's see how it works. When you're negotiating rocks and ruts, it's all about torque. The strength of the wheel's rotation. The more you've got, the better. And the power for it starts with the Thundercat's engine. 950 cc's certainly sounds big, but this power plant is not just about size. Its cylinder heads look like a baseball cut in half. This hemispheric design allows more air and fuel into the combustion chamber, and the shape of the valves help move this potent mixture in and out fast. That buys you low-end torque, so you don't have to gun the engine to do this. Power under control. It's what you need to negotiate steep inclines and maintain traction going through water and mud. The key is to give the wheels power without spinning them out, even at triple the torque of other stock machines. When you gun the engine, you get variable speeds on the wheels with a full range of control, from a slow crawl to a blast-off launch. How does the Thundercat do it? For that kind of control, the transmission needed a rethink. Mechanical transmissions only allow a few different gears to choose from, which means when you change them under load, the wheels get hammered with a jolt of power on every shift. Instead of installing a heavy, cumbersome gearbox, Thundercat designers installed a continuous variable transmission, CVT for short. A drive belt sits in a V-groove on a wheel connected to the engine. As the engine revs, centrifugal force drives an inner wheel in the V-groove to the center, forcing the belt higher towards the edge of the wheel. At high revs, it's like a larger or higher gear. At low revs, a small or low gear. Totally variable. So the Thundercat can power up these rocks at a crawl and kick it into high gear on demand without bucking, slipping, or spinning out. ATVers aren't really ATVing unless they get airborne. But when fast-spinning, high-powered wheels hit the ground, the sudden spike in traction and torque could do serious damage to the drive shaft and axles. So they installed a spike load dampener, a clutch system that cuts off the connection between the engine and axle on harsh landings. Once the engine revs down, the axle is re-engaged and power is restored to the wheels, sparing you a broken ride and a long walk home. To make sure this machine keeps a straight line when blasting through water or mud, a limited slip differential helps all four wheels adjust quickly to keep it moving and on the trail. It's easy to see when skidding or turning corners. The outside wheels actually spin faster than the inside ones to compensate for the extra distance they have to travel. Even with limited slip, a wheel that loses contact with the ground spins wildly and cuts torque off from the other one. Now you're stuck. But on this machine, the rider flicks a switch to lock the differential between the wheels so that they spin together. This gives the wheel on the ground or in the mud all the torque it needs to get in and out of trouble. Finally, how do you design a suspension system to keep the frame intact and the rider upright? Start with one of the strongest suspensions ever put into a production ATV and lose the sway bar. Most ATVs use a solid bar to link the rear shocks. It prevents one set from dipping too low on turns, a rollover hazard. But Thundercat's builders didn't want the loss of control that comes with a sway bar. So it got thrown out in favor of fully independent suspension. This allows one wheel to ride high over a rock without pulling the other one off the ground. Without a sway bar, Thundercat turns are kept stable in two ways. First, a AA suspension stops the wheel from riding up on its edge even during a harsh turn. And stiff steel mesh lining on the tires minimizes body roll. Pretty much as stable as a sway bar and a lot more fun. A machine like this couldn't do what it does without breaking a few ATV rules. Sure, it gets the machine into trouble, but only the good kind. It takes about 300 liters of water to wash your car at home. The average automatic car wash uses about 150. But the latest tunnel car washes are able to get the job done with less than 10. Not only does this new style wash recycle almost all the water it uses, it's also got the latest gear to protect your paint job. Let's see how it works. The tunnel car wash is a familiar machine. Spray nozzles soak, soap, and rinse. Fabric brushes do the scrubbing. Hot air dries the surface. But they have a few sticky problems that are tough to beat. Scuffed wheel rims from metal guide rails, swirl marks from dirty brushes, and water spots from the rinse job. The designers of this car wash wanted to beat all three of these challenges and save water in the process. It all starts here, where cars line up for the conveyor. The synthetic yellow guide rail sets up the front tires without leaving a mark or scratching the rims. They're made with ultra-high weight molecular plastic. It's got extra long molecules that weave together like a pile of spaghetti. With no open ends for anything to stick to, you get a slick, scuff-free glide like riding on a greased rail. Once on the belt, a sensor tells these rollers to pop up and push the car's back tire. Now it's time to start cleaning. And that's about more than shine. The dirt on a car actually increases aerodynamic drag and lowers fuel efficiency. To get rid of it in a way that doesn't damage your car is the goal of every wash. If a fabric brush picks up and holds onto dirt, it will grind it into paint surfaces. So this pre-rinse is designed to attack the dirt from every angle. A computerized timing system and a stream of compressed air controls the nozzles. The brains and lungs of this machine live in a back room, and it drives almost everything with air or hydraulic pressure, not with electricity. It's cheaper to run that way and a lot safer than mixing electricity with water. Even after the first layer of dirt is rinsed off, there's still a thin layer of hard-to-see stuff sticking to the paint. You need scrubbing power to get rid of that. And even dirt as fine as powder can scratch. Cloth brushes on the spinning wraparound system take care of vertical upper surfaces, while dangling cloth washers, called mitters, sweep up the gaps. The trick to avoiding scratches lies in the fabric. This fuzzy polyester can't absorb anything, so there's nothing that can scratch your paint. But it does trap suds between its fibers long enough to drop it on the car and wipe it away. Next, the spinning heads kick in for the car's lower panels. These ride close to the road and pick up a lot of grime that, if not handled properly, will scratch your car. Old-style spinners had hard bristles, lots of friction, lots of cleaning power, but because they absorbed dirt, they did lots of damage to paint. So today's tunnel washes use a soft foam material. These closed-cell brushes resist water absorption and the dirt that comes along with it. Like the mitters, no dirt means no chance of scratching. Down here at tire level, dirt particles are at their heaviest, so the wash needs tough bristles to get them clean. The ones here are pre-worn and only ever touch the tires. It's called a poodle brush. In a lot of car washes, you'd be hitting the dryers at this point. But this machine is about to attack performance-robbing dirt that gets trapped in cars' cooling systems and brakes. Dirt and bugs trapped in the grill can affect engine cooling. So these brushes give it a second wash. They spin opposite to each other to avoid damaging license plates. Then, some clever engineering attacks dust behind your tire's rims. It's called a pendulum washer. When the front tire hits this bar, it carries spinning washers along with it, blasting the hubcap and brakes clean without messing up your rims. The bar slips into this recessed area, then pops out to the back wheels to start again, just like a swinging pendulum. Momentum helps out with the final cleaning step. A small nudge from your car pushes up one last brush before the final rinse, where a soft rain shower takes off all the soap. By design, falling droplets land gently and roll away. And that means no water spots from splashing like you get in a regular wash. Finally, after 90 seconds of pounding action, it's time to get dry. These fans hit your car with intense air pressure. When ready, they slam open to blow off the water, which doesn't go to waste. Your car may be done, but this machine has one more job to do. Take care of that water. Almost all the used water flows through these grates into underground tanks. First, the dirt is filtered out. Then the water is sanitized before returning to the main storage tank. Up to 80% of the water is reused. This tunnel car wash has put a new spin on an old idea by delivering a near-perfect clean while keeping cars and their drivers' reputations intact. No city skyline would reach these heights if it weren't for this machine. Before the elevator, buildings rarely grew over 5 stories. They perform billions of rides every day around the world. Among the safest ways to travel, there's less than 1 chance in 12 million that something will go wrong with the elevator you're riding in. Let's see how they work. The most popular elevator design is the roped elevator, where a car is raised and lowered by steel cables. The machine's muscle lives up here at the top of the elevator shaft. Its ropes attach to the car and loop around a shiv, a pulley with grooves to grip the ropes that's connected to an electric motor. Turn the motor one way, the elevator car goes up. When the motor turns the other way, it goes down. A counterweight lives on the other end of the ropes to offset the weight of the car. It's usually about half the weight of a fully loaded passenger elevator. So, on an average ride, the two are perfectly balanced. All the motor needs to do to move the car is provide a nudge to tip the balance one way or the other. This system saves energy as well as wear and tear on moving parts. Once the car is moving, the motor's only job is to control one of the 2 falling objects. Both the car and counterweight are attached to guide rails inside the shaft. They keep everything from swaying back and forth and also give a backup set of brakes something to grab onto. If anything goes wrong with the motor, hydraulic fluid is cut off, and that automatically releases this brake that seizes the ropes for a quick stop. Technically, one of these steel ropes is enough to hold up both the car and the counterweight. The rest are there for backup, in case one snaps. But what if the whole set is cut? Don't worry, it still won't plummet. This machine has a built-in failsafe. There's a governor located beside the motor, with its own pulley and separate cable attached to the car. There are 2 spring-loaded metal hooks called flyweights inside the governor. If a car free falls and the governor spins too fast, Centrifugal force pushes the hooks out. They seize ratchets on the fixed inner rim and stop the pulley. The governor's rope jerks on an arm on top of the car, and this locks the brakes. Okay, that takes care of safety. Why do we have to wait so long for it? Call buttons send signals to the elevator's computer. It keeps track of every car in every shaft through sensors on the shaft wall, then calculates which car stops where and when. It's a lot to keep track of. Newer systems can sense a full elevator car. If it's too heavy, it'll skip your floor and come back when it's ready. The idea of the rope elevator is simple enough. One side goes up, the other goes down. It just took a couple of thousand years to figure out how to stop it. It's easy enough to drive, but without brakes, we'd rather walk. If one machine defines our self-serve culture, it's this. The very first ATM opened in New York City in 1939. But it's only in the last 20 years that it's taken over. And it's got a lot of names. Automated teller, banking machine, cash point, or simply a money machine. The one we're looking at is an automatic teller machine, or ATM. And like the bank teller humans it replaces, the ATM identifies you, knows your limits, and provides access to financial transactions. It's also pretty much impregnable. Let's see how it works. ATMs face several challenges. First, make sure you and your card are legit. Second, find your account information. Third, accurately complete the transaction you want. And finally, do it all while protecting an onboard vault that stores thousands. The machine starts by checking your credentials. This black stripe looks solid, but the ATM has two readers that see what you don't. 1 million tiny magnets, each with a positive or negative charge. A binary code. The first reader looks for a special code that confirms the card is real. The second reader grabs your account number and password to check against what you've just keyed in. Once your password is confirmed, the ATM connects to your bank's network, and it gives the machine its marching orders and remotely controls access to the onboard vault. Trays in the vault hold different denominations, with up to 1,000 bills in each. One tray is left empty for deposits. When you drop in a check or money with an envelope, it goes into a bin and is manually sorted later. Some ATMs, like this one, can take deposits without an envelope. It's able to hand count bills. This also allows the machine to refill itself. For withdrawals, vacuum-driven suction cups grab one bill at a time and feed it out through a roller system. Delivering bills one by one from the vault keeps you from getting overpaid. This machine is a very careful counter. As each bill squeezes through these rollers, sensors calculate the width of the paper, about the thickness of a coat of paint. Any thicker, the machine figures that 2 or more bills are stuck together. Any thinner, the bill's worn or fake. Either way, the sensors catch it, and the bills get sent to a reject bin. That's likely what's happening when you hear a pause in the machine's counting. The dispenser slot hands over your cash. Your bank's computer records the deal and then tells the machine to return your card and give you a receipt if you want one. Safe and secure. With more than 1.5 million ATMs around the world, most of us simply take our access to cash for granted. And crooks know it. Thugs go after them with blowtorches, crowbars, and trucks. But they don't stand a chance against this machine. Built from over 100 kilograms of steel, able to withstand 22 tons of blunt force. The vault can survive assault more than long enough for police to arrive. And even if they get into the machine, the money's useless. Exploding canisters of dye ruin the cash as soon as the vault's seals are broken. There's also onboard GPS to track the geniuses who try to haul them away. Brainier crooks use an electronic sleight of hand. One technique is to insert a false card reader or skimmer into the card slot and stick a tiny spy camera over the keypad to steal your password. Foiling them is as simple as protecting the number you enter. It took a long time for automatic tellers to evolve into the trusted machine it is today. And until we stop using cash altogether, this intelligent dispenser will continue to take our orders and track them with amazing accuracy. This firefighter is built to swoop onto lakes and rivers, fill up, then hit fires with water bombs. The Combine is a mobile processing plant that spits out 200,000 kilos of corn in one day. Hold your breath. The wind tunnel cranks out a typhoon to make sure the skyscrapers we live and work in stay upright. The 50 cal machine gun has been a military favorite for 90 years, thanks to its deadly reliability. Let's take the lid off these machines and see how they work. This is the Bombardier 415 water bomber, also known as the Super Scooper. It's a flying boat that's the backbone of firefighting missions around the world. Whether dousing blazes in remote Canadian forests or protecting hillside homes from raging California wildfires, it's proven itself to be one of the most powerful aerial firefighting machines ever made. It can pick up over 6,000 liters of water in one scoop. This translates into over 100,000 liters an hour being poured onto a nearby fire. 3 tanker trucks worth. Let's see how it works. To make a water bomber, all you gotta do is combine the floating ability of this, the cargo capacity of this, the maneuverability of this, and then throw in a little bit of this. A big challenge for engineers. The 415 does it with a wingspan almost as long as a 737's, 2 powerful variable pitch turboprops, a rust-proof aluminum hull, and massive water tanks fed by hydraulic rams. The first challenge for the 415, get airborne quick, even from the smallest runway. These machines have to be able to get up and down fast on land and on water. That happens thanks to these wings and these engines. The wings have a surface area larger than a jumbo jet's for extra control and lift. They're designed with a highly arched shape or camber and huge flaps. These give the 415 better stability and lift at slow speeds. So much lift that its tail section is oversized to help keep everything balanced. The power for this machine comes from 2 2,500-horse turboprops. A turboprop engine is simply a gas turbine. Inside, the air is compressed, mixed with jet fuel, and set on fire. As it burns, the air expands. The expanding air spins a turbine that spins a drive shaft, which turns a gearbox and the propeller. Attached to the front of the engines, these propellers have variable pitch blades. The blades' angles can be changed. This allows the engines to hit high RPM while the plane is parked, effectively revving the engine while in neutral. Then, with a change in pitch, pilots can blast the plane off the runway. This lets the 415 take off at just 150 kilometers an hour. about half the minimum takeoff speed of a passenger jet. And that high power at low speeds comes in handy when it's time to hit the water. As the 415 approaches its target, it lowers the flaps and reduces the pitch on the propellers. This slows the plane down to about 140 kilometers an hour, a speed that would cause most other planes this size to stall and fall. The 415 is now a boat with wings. Crafted from marine-grade aluminum, it even has special airtight compartments to keep it floating if it hits something and gets punctured. When collecting water, only the bottom few centimeters of the craft get wet. Technically, it's still flying, and the pilot still has maximum control. On the water, these machines can swerve to avoid obstacles, or even gather water from a winding river. And these water scoops are way too small to suck up a scuba diver. Hydraulics push out the scoops when it's time to collect. The plane's speed is all that's needed to ram the water into its tanks. It fills up in just 12 seconds. Then the scoops retract, and it's takeoff time. The 415 can climb at angles that would knock other planes from the sky, which is what this machine needs to fight fires. If it's a small fire, the scooper just dumps directly onto the blaze. It flies low, just above the target, opens its 4 doors, and dumps its entire load in 1 second. Dropping over 6 tons of water, the pilot's gotta be accurate. That amount of liquid could cause some serious damage to someone on the ground. But even that much water is no match for big wildfires that can burn at temperatures over 1,000 degrees Celsius. So the 415 changes tactics and injects the water with foam stored in these tanks. The foam is a synthetic biodegradable fire suppressant. When the 415's doors open, the supercharged water hits the air and transforms into a thick foam, blanketing an area the size of a football field. The foam sticks to trees and the ground for up to 30 minutes and creates a wall of water. With a few well-aimed shots, a single 415 can create a 2-kilometer-long fire break. Its doors can even be programmed to release one at a time, spreading foam over an even greater distance. And since it can pick up water from almost any source, even a river just 2 meters deep, this machine can load up, dump, and refill in as little as 2 minutes, which translates into 100 dumps in 4.5 hours flying time. Over 500,000 liters of water. Despite its ungainly appearance, it really is a beautiful flyer. And once it gets airborne, there's no doubt about its primary purpose. This is one serious firefighting machine. This is a combine harvester. A machine that harvests grains like wheat, soy, and the king of the modern field, corn. It's probably the most important machine working on farms today. And without them, there'd be a lot less food to go around, and a loaf of bread would cost a small fortune. Corn is a linchpin of the modern food chain. It shows up in almost everything we eat, from sweeteners to farm salmon. And a combine this size gets through about 80 acres of corn in a day. You'd need hundreds of experienced pickers just to cut that many ears by hand. And that's only one part of the operation. This machine takes less than a minute to strip and collect over 2 million kernels of corn. Let's see how it works. A combine gets its name from merging or combining a bunch of jobs that used to be done by separate machines or by hand. When harvesting corn, it cuts the crop from the ground, separates the stalk from the cob, and then sends those cobs into a rolling drum to strip off the husk and kernels. It costs hundreds of thousands in fuel, seeds, and fertilizer to plant this crop. And once it's ready for harvest, farmers can't afford to waste any of it. So this machine has to get it done fast without wrecking the crop or itself. First up, remove the ears of the corn from the stalk. For that, you need a special attachment called a corn header. It snaps easily onto the front of the machine. The header has gathering points that fit between the rows of corn. The fields are planted to mesh perfectly with the headers. In this case, rows of 6. This allows the combine to go back and forth with maximum efficiency, gathering as much corn as possible with each pass. With the help of careful planting and the right header, a combine can harvest about 400 tons of corn in a day. The stalks are channeled toward pairs of chains. Teeth on the chains push the stalks into 2 spinning rollers. The rollers pull the stalks down. The cobs are too big to fit, so they snap off. Below the rollers, spinning blades turn the stalks to mulch, and another set launches them out the back of the combine. Knocking the heads off these things is only part of the challenge. Next up, stripping the seeds. This auger spins the cobs toward a central conveyor belt that carries them to a curved metal grate called a concave. It wraps around a meter-long rolling drum. The rolling rubs off the husk. Then the sharp edges of the concave strip the kernels from the cob. The kernels fall onto a vibrating grate. This powerful fan blows air up through the grate, and the air plus vibrations force the plant debris and husks to the top, while the kernels fall to the bottom. An auger carries the kernels up to a grain bin, while the rest of the material is sent back onto the field, where their nutrients are returned to the soil. When the grain bin is full, it simply dumps its load and goes back for more. This machine makes it look easy, but it has to constantly adjust to different conditions to find the perfect speed. If the combine goes too fast, it loses yield because this processor on wheels can't keep up with the corn. And too slow is, well, too slow. So as it works, sensors feed information into the cab. The flow sensor reads grain impact force from the top of the clean grain elevator to calculate the volume of corn. Grain moisture and temperature are measured with this sensor. An electrical current flows from the sensor fin through the grain and calculates its humidity. All this information is fed into the cab to keep the operator constantly updated on how much corn is being harvested. And that's not the only data at work up here. These machines never get lost. The route they follow is controlled by an onboard GPS system that ensures no-fault harvesting. The combine is a perfect blend of farming technology and mechanical know-how. An ultra-efficient machine that does everything we ask of it to put food on our tables. A wind tunnel is a machine used to research the effects of air moving past solid objects. For centuries, they've helped scientists and engineers experiment with all kinds of subjects. From understanding the principles of flight to making faster race cars. Weather simulations inside wind tunnels can also provide critical information for building safety. This is more important now than ever, as buildings have become taller and more complicated. The National Research Council's closed-loop wind tunnel outside Ottawa, Canada, is a perfect spot to test buildings. This world-class facility boasts a 9,000 horsepower motor that drives a 12-meter fan. Big enough to create a typhoon, which is why it was chosen to test this skyscraper, the 128-story Shanghai Tower. The Shanghai Tower is a city on its own, with over 4 million square feet of living and working space. And it sits smack dab in the middle of Typhoon Alley. Wind causes towers this tall to lean and sway. They can lose windows, and worse, fall over. So they can't be built without input from the wind tunnel. Let's see how it works. Turn over big engine, spin huge fan, create wind. That's easy enough. But when testing this tower, even a 1/85th scale version, you can't just blow a fan on it to get the data you need to make it safe. Sensors are connected to the model so that engineers can perfect its shape before they begin construction. And the wind tunnel has to be able to create many different types of conditions to mimic the real world and make the testing worthwhile. To replicate a steady flow of wind, fixtures in the tunnel are as smooth as possible to help control turbulence. The fan actually sucks air away from the model, around the donut-like structure and back. Every time the air circulates through the fan, it picks up speed. It also picks up a lot of unwanted turbulence. An uneven airflow ruins testing. So the less turbulence there is, the better the results. Turning vanes in the corners help smooth out the flow. But that's not enough. So the tunnel draws heat from the air with fans in these cooling towers. Then, the air passes through mesh or honeycomb screens that further calm it. And finally, it passes through a settling chamber, where the swirling air currents spread out and subside before carrying on. Once the air is smoothed out, the wind tunnel needs to create its own custom turbulence to simulate real-world conditions. And they use a net to do it. The netting creates turbulence that mimics airflow through tall buildings. Now we're ready to see what the building will do in a windy city. The fan in the wind tunnel takes about 5 minutes to hit top speed and deliver 200-kilometer-an-hour winds into the tower's outer skin. The first design challenge measures structure strength and dynamic response, which includes how far the building sways back and forth. To measure these, the model is securely bolted to a floating table. Beneath it lies a room packed with sensitive measuring devices. As the wind pushes against the building, these weights move to counter the force. When the table is pushed in one direction, the weights move the other way to keep it balanced. The further they move, the greater the force. It's all linked to a set of levers that come up with the final measurements. This data tells engineers what kind of damping systems to install in the tower to control excessive movement. Now, wind changes direction all the time, but the model is secured to its base. So the whole table rotates into the wind to measure every angle of attack. Now the machine has to test the integrity of the building's outer surface. These tiny holes connect to hundreds of tubes, and those connect to pressure sensors that measure wind load. As air flows around buildings, it creates small swirling currents like water flowing around a rock. This can put tremendous strain on materials as the air currents break from the building. Sensor data lets builders know where to strengthen materials or install special fixtures to disrupt wind flows. Small foundations, great height, and odd shapes. Today's towers could never make it from the architect's imagination to the real world without the wind tunnel. A machine that keeps urban residents high, dry, and safe, even when a real typhoon hits. Meet the Browning M2 50 caliber machine gun, affectionately known as Ma Deuce. The first version of this machine arrived on the scene at the end of World War I. Its simple, reliable design and its ability to smash through steel and concrete is why the M2 is still being used by armies in every corner of the world. Let's see how it works. Bullets linked by small metal clips are loaded into the breech. When you cock the gun, a round is snatched up and dropped into the chamber. Now the firing cycle begins. On the M2, the trigger is pushed. This starts a chain reaction that sends the firing pin flying towards the back of a shell. When it hits, a primer is ignited, setting off a small explosion. Up to 55,000 pounds per square inch of force is generated when the shell ignites in the chamber. The force of the explosion slams the breech bolt back. This action forces another round into the chamber, and the process starts over again. All driven by the energy exploding from the shell. After the bullet fires, the extractor grabs the rim of the empty shell, and a spring-loaded ejector punches it out the bottom of the gun. The M2 is air-cooled. Its open breech allows heat and smoke from the firing cycle to vent. Inside the barrel, a process called rifling has grooved a pathway roughly 1 turn every 30 centimeters. As the bullet is forced through the barrel, it follows the corkscrew path. The path puts a spin on the bullet that maximizes its flight accuracy and increases the damage on the receiving end. The bullet easily breaks the sound barrier, exiting the barrel at 900 meters per second. That's over twice the speed of sound. Not bad for a round this big. And the M2 can fire a bunch of different types of ammo. Standard ball, tracer, armor-piercing incendiary tracers. These guys have strengthened casings and a hard nose to punch holes in thicker armor. The tracers leave a flash of light from a small pyrotechnic charge in their base. Once ignited, it burns like a firework, making the bullet visible to the naked eye. Tracers are usually loaded 1 in every 5 rounds. This helps the gunner visually follow the path of the bullets. And the M2 is capable of firing up to 500 rounds per minute. But at that rate, the barrel would quickly overheat and begin to warp. So in standard combat, the gun is fired at a rate of about 40 rounds per minute, in short bursts. Uncompromising firepower and combat reliability are just 2 reasons why this machine has withstood the test of time. The latest trams generate electricity while braking and send it up the line to help power trams behind it. Flying a helicopter is a delicate balancing act between 2 rotors. But hauling tonnage and catching crooks takes a special breed. It looks like it can read our thoughts and predict our moves. The science behind the Segway transporter. This 3D printer is a real-world replicator. Feed it pictures, it manufactures objects in 3 dimensions. Let's take the lid off these machines and see how they work. Depending where you're from, this is a tram, a trolley, or a streetcar. Whatever you call it, the urban railway is making a comeback. At one time, almost all city transit ran on rails. But then, buses and cars took over. New technology, no emissions, and ease of installation has given this form of mass transit a new lease on life. Trams run on electricity, and the latest versions can actually generate some of their own power. Let's see how they work. Choosing low-emission trains over gas and diesel power is great for PR and government pocketbooks. But for this ride to appeal to the masses, you need more than that. To be #1 in the public eye, you have to be efficient, reliable, and comfortable. Let's start with efficiency. Compared to other forms of mass transit like buses, trams need a lot less energy and maintenance. Their electric motors are more powerful, quieter, and efficient than their gas-guzzling cousins. Trams get power from overhead lines fed by the local grid through something called a pantograph. It draws electrical current through points of contact. Early versions of this device had a problem. Constant rubbing from overhead wires wore out contacts and cut off power. Now, overhead lines are laid out in a zigzag pattern. So the pantograph slides side to side while the tram is in motion, greatly extending the life of its contacts. Electricity flows from the wires to copper coils inside the motors. This creates a magnetic field that spins a magnet, and with it, the wheels. This machine can top 100 kilometers an hour, but rarely goes above 70 while working in cities. And that means it needs good brakes. But these ones aren't just for stopping. They also help feed electricity back into the system. A design feature that can save big on a city's power bills. When the machine needs to stop, the power is cut off to the motors, but the tram's momentum keeps the wheels spinning. And this allows the motors to generate power. It's called regenerative braking. The momentum spinning inside the motor creates an electric current that's sent back up through the machine, through its pantograph, along the overhead wire, and into the nearest tram. An electrical piggyback ride. And if the tram needs to stop in a hurry, it's also got sets of air brakes. In an emergency, say if something falls in front of the tram, the brakes all work together with a safety bar to prevent anything from getting stuck under the machine. Step 2 in winning over the public is reliability. And that means not breaking down. With no transmission, no potholes to deal with, no tires to go flat, and no fuel to run out of, the only thing that really threatens this ride is a power failure. Trams like these do cost a lot more to purchase than buses, but they last decades longer and cost much less to run on a day-to-day basis. Coming across as good for the environment and city bank accounts is fine. But it doesn't explain why the average person prefers light rail to buses. For that, you need to look at this machine's third advantage: comfort, and style. New models come with street-level ground clearance for easy on and off. They can grow with extra cars to give plenty of rush hour elbow room. And with steel wheels that can be kept true, the ride is super smooth. The low ride comes courtesy of a design that hides most of the tram's components on the roof, giving the wheels and axles plenty of room to provide support. Super strong pivot points seamlessly join the cars together and enable these machines to take on up to 7 cars and still slide through corners. Accordion-like rubberized material fills in the gaps around the joints between the cars. It's rush hour, and now you have transit that's easy to board with continuous open space for over 200 passengers. Keeping a ride smooth has always been a challenge for machines that depend on steel wheels riding steel rails. And the wheels wear out fast, especially under a tram that has an empty weight of over 40 tons. So every 20,000 kilometers, they get a tune-up. A diamond-tipped truing machine. This big robot shaves off 0.5 millimeter thick strips until the wheel is perfectly clean and level. It guarantees a smooth ride and reduces friction, saving big on electricity. Fast, smooth, and cheap to run. With cities increasingly building more right-of-ways for the tram, the other options are looking a little older every day. Helicopters are hard at work all over the place these days. With great speed, range, and a lifting capacity of over a ton, machines like Eurocopter's Twin Star and B3 are fast enough to work for police, strong enough to haul for utility companies, and nimble enough to work in tight places without going down. These Hydro 1 pilots make it look easy, but flying a helicopter is anything but. Picture balancing on a large ball with a machine that weighs over a ton. To fly one of these, you have to control the 3 dimensions of pitch, roll, and yaw. Let's see how it works. An engine spins a rotor. The rotor spins blades, and up you go. A helicopter is an assembly of thousands of loose pieces trying to fly in formation. Getting them to work together to create the most versatile flyer in existence is the hard part. The first challenge is to create lift. The second is to control it. And the third is to keep it from crashing if the engine fails. First up, lift. The blades of a helicopter's main rotor are basically wings that slice through the air. They're shaped like the airfoils of an airplane wing. But these are much thinner and narrower because they have to spin extremely fast to get airborne. And to do that, they need a slight shift. This change in the blade's angle of attack, combined with their speed, forces air down. When the amount of air forced down overcomes the weight of the machine, it takes off. Helicopter blades need heavy air to create lift. The higher you go, the less air pressure there is, and the harder it is to climb. On to challenge number 2, control. Spinning the main rotor this fast is terrific, but it comes with problems. For starters, the body of the helicopter wants to spin in the opposite direction of the rotor. To control the machine, a precisely located counterforce is needed for balanced flight. And on a chopper, that comes from the tail rotor. On this machine, it's 1/6 the size of the main rotor, so it spins 6 times faster to balance the force from the big blades. The power for all this spinning comes from a high-performance engine that sucks oxygen into a combustion chamber to burn jet fuel. This produces super hot exhaust gases that drive a turbine. And it turns drive shafts that connect to the main and tail rotors. The drive shafts are linked through gears to a transmission that keeps everything in perfect sync. So now you've got basic control of a powerful flying machine. Let's take a closer look at some of the finer elements of helicopter handling. A twist throttle controls the engine power to the main and tail rotors. Once airborne, the rotors spin at a fixed RPM all the way. Pilots never hit the gas to go higher, faster, or to change direction. The fixed RPM is set to maintain perfect balance between the two rotors. A helicopter's ability to fly in 3 dimensions is all about the blades and their angle of attack. And that's controlled with the collective and the cyclic. They allow pilots to change course, altitude, and speed. The cyclic is the control directly in front of the pilot, which he uses to move left or right, or to go forward or back. When you push the cyclic forward, the angle of the blades increases at the back and stay low at the front. This creates an imbalance of thrust and propels the craft forward. Same thing happens when you push the cyclic to the side. You get an imbalance of thrust and move sideways. The collective is located in the center of the cockpit. The pilot raises or lowers this control to go up or down or to change speed. And these signals stay in sync with all the spinning blades through the swash plate. 2 discs with a set of ball bearings in between them. When the bottom disc pushes up, its movement passes on to the spinning top disc. The more it's pushed, the more the swash plate pushes up each rod, changing the angle of attack for each blade. While all this is going on, pilots use foot pedals to control the angle on the blades of the tail rotor. All the forces applied to the main rotor blades have to be counteracted. Collective, stick, foot pedals. A very delicate balancing act that keeps everything from spinning out of control. On to the third challenge, staying in the air when something goes wrong. What happens if the engine suddenly conks out? If you figure it just drops like a stone, you'd be wrong. To fly one of these things, you gotta learn to land it when the engine quits. And they pull that off with auto rotation. If they lose power, pilots let the main rotor spin freely. The blades are flattened out to catch max air, and this usually provides enough control to glide safely to the ground. Remember the thousands of parts bit? Well, some are more important than others. If you lose your connection with the blades, you're gonna drop like a stone. There's no backup plan for this malfunction. On helicopters, that comes down to some very important nuts, the main thing keeping the blades attached to the machine. But losing them is never a problem on well-maintained machines like these. When you put a great helicopter in the hands of a crack pilot, there's nothing to fear. Just enjoy the ride on the most maneuverable flying machine in the world. Since its unveiling in 2001, the Segway has captured our imagination and pointed to the future of transportation. That's because this machine seems intelligent, impossibly keeping us balanced while mysteriously reading our intentions when we want to move, stop, and turn. No, it's not magic. But that doesn't take away from the cool stuff that goes on inside when you ride this thing. Let's see how it works. The Segway is an electric scooter with lateral wheels. So it's a machine that has to copy what we bipedal humans do and learn to stay in balance. As you lean forward, gravity wants to take you down. And it would, except the Segway's wheels automatically pick up speed to keep the platform beneath you. Same goes for reverse. Lean back, and that's where you go. The wheels have to spin in that direction to keep you from hitting the ground. So, from the moment you step on the Segway to the moment you get off, you're basically falling. Even when keeping it stationary, you're really falling forward one moment, backward the next. The wheels keep catching you before you hit the ground. Balance and movement are the same thing on this machine. So how do the wheels know what to do? To help keep us upright, the human machine comes with legs, muscles, and a brain. Same goes for the Segway, in the form of wheels, motors, and a really clever little box that's crammed with sensitive measuring devices. 5 angular rate sensors detect changes in direction and speed, and tilt sensors detect angles. They work the same as a carpenter's level, except the liquid inside conducts an electrical signal. Together, these sensors provide data that allow the machine to determine if you're about to tip over. It sends the commands to the wheels and keeps you upright. No matter which way you lean, they're always one step ahead of you. The Segway has 10 microprocessors, giving it about 3 times the brain power of a typical PC. You can't outsmart this machine. To turn, push the control stick to one side. This decreases power to the inside wheel, spins the outside one faster, and round you go. Segways have a carrying capacity of up to 118 kilograms. Each wheel comes with its own 2-horsepower emission-free electric motor. Gearboxes inside the wheel assembly step down the motor's RPM for smooth control and a distinctive whirring sound. The gears also help limit the Segway's speed to about 20 kilometers per hour. But even at that rate, you'd do some damage if something went wrong and you flew over the handlebars. So the machine comes with backup systems that shut it down safely if there's a glitch. There's no tumbling off this guy. When you're done for the day, just ride over to a wall socket, plug it in, and in no time, it's ready to ride again. And these days, that includes everything from off-road trail riding to making a day of foot patrols a little smoother for police. This machine may not rule our sidewalks yet, but it's finding a way into our transport systems one lean at a time. This is the Z-Core Spectrum 510. It's technically called a 3D printer, but we're going to call it a replicator. This machine that looks like a photocopier prints objects in 3 dimensions. Simply upload a digital picture to get a solid object up to a cubic foot in size. Let's see how it works. This machine makes anything from action figures, architectural models, inventions, even a prototype running shoe. And they all come from exclusive design software that speaks the printer's language. In this case, an online gamer wants to take his action figure from virtual to real. To start, feed the printer with a digital 3D file. The printer's processor dissects the 3D image like a CAT scan, slicing it into super thin layers, about 1/5 of a millimeter each, close to the width of a human hair. The shape of each virtual slice is translated into mathematical coordinates and plotted out, a bit like how GPS uses math to build virtual maps. Once the design is loaded and analyzed by the printer, the replicating can begin. A roller moves a thin layer of powder from a feed bin into the printer's build chamber. The powder is a mix of plastic compounds that have to be of a certain hardness and elasticity. When dry, it has the consistency of talcum powder. Once the first layer of powder is laid down, the print heads go into action. They lay down color ink onto the first layer according to the object's coordinates. But this machine doesn't just lay down ink. To build in 3 dimensions, it needs an adhesive or binder fluid to start the foundation for the final object. Layer after layer, they're glued together. The build chamber lowers with each pass, and the next thin layer of powder is added, ready for more ink and more adhesive. This continues 1 layer at a time until the entire model is complete. The object's color is created by mixing 3 primaries of ink held in these reservoirs. That sends them out through 3 print heads. While a 4th carries clear binder fluid. This allows the machine to create white when necessary. Here's a completed print job. It comes out as a thick block of powder, but watch as the powder is blown away. Buried inside, solid figures. The surrounding powder holds up the objects as they're being constructed. The excess stuff is reused for the next printing. Nothing is wasted. Like an archaeologist wiping away the dust on an artifact, our newly printed subject is revealed. The figure gets a once-over by hand and is dunked in sealant and dried. One of these printers can crank out about 16 of these every 5 hours. Imagine how long it would take to make these by hand. Architects and engineers use this machine for everything, from scale models to machine prototypes with parts that move. If a regular printer is a painter, the 3D printer is a sculptor. And a version of this may be in your home soon enough. If you can imagine it, this machine can make it. This plant has dozens of machines that turn rock and stone into cement, concrete's essential ingredient. This machine moves people and cars across some big water. The Super C-Class double-ended ferry does it best. A raging jet fuel fire burns up a plane in seconds. To put it out, you need a special firefighter with some reach, the Oshkosh Striker. Let's look inside these machines to see how they work. This is the St. Mary's cement plant on the Canadian shores of Lake Ontario. Cement is the essential ingredient in concrete. Concrete is basically sand and gravel. Cement is the glue that holds it all together. And plants like this one have to be able to make a lot of it, because we need a lot of it. The world uses about 3 billion tons of it every year. The recipe? Crush piano-sized rocks, blast dust through man-made tornadoes, and cook it into a molten lava. All to make a material that's built the world we know. It's the most versatile building material in the world. So this plant's machines run weeks on end, day and night, without ever stopping. Let's take a closer look. To make cement, you need to measure out some crushed limestone, sand, and iron, and cook it up in a big oven. The end result? Super powerful glue that's activated with water. The basic recipe for cement is simple enough. What's tough is making huge amounts real fast without making a mistake. One tiny error in the formula ruins the whole batch. So what makes limestone so special? Cement needs calcium. And limestone started out as the calcium-rich shells and skeletons of small prehistoric ocean dwellers. It's the calcium in cement that gives it properties necessary to help form concrete. And it's the cement plant's giant pestle and mortar that starts the rock crushing. Giant pieces of rock are dumped into it as the center cone sways back and forth to break it up. In seconds, this machine reduces a rock as big as your dining room table to chunks the size of a grapefruit. The trick to keeping this all going is a steady supply of rock. No way you could ever ship this stuff and stay in business. That would cost way too much. So for a cement plant, location is everything. This is the limestone quarry next door. When it runs dry, the whole shooting match has to pack up and move to a new location. To get at the limestone, it's hacked off layer by layer in an open pit. Explosives are packed into precision-drilled holes along the mine's leading edge. The charges are set off like dominoes, all of them detonating in less than a second. One blast frees up 50,000 tons, which will keep this crusher fed for up to 5 days. The chunks fall from the primary crusher onto a conveyor belt for further refinement. But the rock still has to go through 2 more crushers before it's reduced to a dust so fine that it could pass through your home coffee filter. Next step, the rocks are delivered to the hammer crusher. And it beats them into golf ball-sized chunks. Now, add iron and sand. The mix has to be perfect, so machines monitor it every second. They can adjust the mix on the fly or send warnings to a control room. Now, it's time for the final crusher. And it's a big one, more than 5 stories tall. The mixed rock is driven under 50-ton wheels that do the crushing. If the amount of rock gets too low, sensors tell the conveyors to pick up speed. A huge vacuum sucks up dust from the crusher and sends it to these hoppers. From there, the dust is screened for impurities and stored in one of the world's largest silos. Mix water with what's in here, and all you'll get is gray muck. This stuff is still just rock dust. To become cement, it has to be superheated, then mixed with more ingredients, on its way to becoming the ultimate construction glue. Heat is the critical catalyst in setting off a chemical chain reaction that turns the raw mix into the real thing. The stuff that hardens when mixed with water. For that to happen, you need to get the carbon dioxide out of the stone. And the best way to do it is to get things real hot, all the way to 1,600 degrees Celsius. That's hotter than the core of an erupting volcano. It starts in this preheating tower. Heat from gas burners rises up through interconnected cones. Each one is 7 meters in diameter and 15 meters tall. The limestone powder swirls down through the rising heat, moving from one cone to the next, heating up as it goes. 5 cones later, it hits 900 degrees Celsius. And that's the magic number. At this temperature, it creates new bonds and frees carbon dioxide stored in the limestone. Next, you need to bond the dust back together by melting it in this kiln. At one end, a giant flamethrower that slides between 2 blast-proof doors. Fuel blows down its length and explodes into flames 10 meters long. Hundreds of air compressors stoke the fire with blasts of oxygen. Advanced thermal imaging cameras keep constant watch. Temperatures have to be kept steady to make sure the product is consistent. And that's just one of the problems maintaining a blaze this powerful in a kiln this big. You also got to stop it from clogging, twisting out of shape, or developing dangerous hotspots that could shut the whole thing down. To prevent backups, the kiln never stops turning. That action keeps the mix tumbling like clothes in your dryer. And since it's designed with a downward slope, each rotation carries the mix a bit further. The twisting force is strongest near the motor and loses torque further out. So these support tires have a flexible inner ring that allows the outer section of the kiln to slip, making up for any lag in rotation and keeping everything turning together. The rings relieve pressure that builds up from the high torque twisting. Without them, the kiln would tear itself apart. By the time the mix reaches the other end, it's a scorching 1,500 degrees Celsius. Machine-made lava. So the kiln has to be lined with ceramic blocks. Hundreds of thousands of them. They're tapered, so when you stack them together, they form a circle, supporting each other like an arch. Even with the blocks, the outside of the kiln can get dangerously hot. So technicians use infrared cameras to locate trouble. Problem spots get immediately blasted with cool air from massive fans. Even then, the heat and friction take their toll, and eventually turn blocks from this into this. When that happens, the kiln is shut down. It takes a full week for it to cool enough for maintenance crews to do the repairs. The bricks last for about 12 months each, giving the kiln enough time to make about 2 million tons of this material. It's called clinker, and it's what you get from all that cooking. Basically, dust that's been partially melted back into rock. The clinker is cooled on vibrating grates in a building connected to the kiln. The material is then picked up by a conveyor and sent on its way to be mixed with the final ingredient, gypsum. It slows the chemical reaction that begins the moment you add water to cement. Both gypsum and clinker are put on precision-controlled conveyors. 95% clinker, 5% gypsum, and fed straight into a rollerball mill. Inside, steel balls pound everything into microscopic dust. By the time these machines are done, the powder is so fine that compressed air simply blows the finished product up these pipes and into storage silos, ready for pickup. Just 3 hours ago, this rock was part of the Earth's crust. Now, thanks to the machines in this cement plant, it's ready to build bridges, roads, buildings, and pretty much everything else you see around you. This is a Super C-Class ferry, a vital transportation cog working the coast of British Columbia, Canada. With way too much water for a bridge between the mainland and nearly 1 million residents who live on these islands, ferries are the only practical way to move thousands of people, their vehicles, and countless goods back and forth every day. This 160-meter, 10,000-ton ship can haul almost 2,000 passengers, 370 cars, and 32 tractor-trailers at the same time, making it and its two sister ships the largest double-ended ferries in the world. And that means more than having two doors. You need two wheelhouses, two propellers, two rudders, and 4 giant diesel engines. And then you need some advanced engineering and safety systems to keep it all floating. Let's see how it works. A double-ended ferry like the Coastal Celebration is basically a floating bridge powered by huge engines. You just drive in one end and out the other. This allows the ferry to load and unload all these cars and trucks in as little as 20 minutes. But this design creates a few problems. Having propellers on both ends is great for getting in and out of port quick, but how do you get them to work together? First up, propulsion. These monster engines crank up a pair of electric generators, powerful enough to supply a constant source of electricity to almost 20,000 homes. All of this energy flows to giant electric motors, one for each propeller. To change direction, just cut off power to one and send it to the other. The machine's propellers have a variable pitch mechanism that gives them total maneuverability. So when not in use, the blades turn and tuck into a streamlined position. That's basically how you make a ship with no front and no back. But the Super C ferries are so big and powerful, they need special engineering to make sure the parts can stand up to the pressure. Each motor spins the propellers with over 21,000 horsepower. That's the equivalent of 600 standard outboard motors, made all the more efficient by a flex cam system that adjusts each of the engine's pistons hundreds of times every minute. All that power puts a lot of strain on the shafts that connect the motors to the propellers. So special oil-filled rings support the shafts and prevent warping or twisting from all that torque. One of the ship's enormous propellers is spinning on the other side of this steel wall, and it's got problems of its own to deal with. One of the biggest is a destructive form of erosion unique to marine vessels. Props this big create lots of bubbles and incredible amounts of water pressure. That's great for thrust and propulsion, but the action is also strong enough to compress air bubbles so much that they superheat and explode. It's a phenomenon called cavitation, and it would chew through the blades if they weren't made from a specially designed alloy that ensures long-term durability. The Super C's designers put a lot of thought into safeguarding mechanical parts on these ships. But what about the passengers? Fire is always a huge concern for ships at sea. Select crew are trained as firefighters, and each ferry has its own team. But if fire breaks out on a ship, you have very little time to stop it before it gets out of control. So in keeping with all the other bells and whistles on this machine, they installed a unique fire protection technology that knocks out blazes before they can spread. Their system combines the suppressing strength of water with a knockout punch of anti-fire gases without risk to passengers or crew. The Super C-class ferries use a high fog system that can put out just about anything in under 5 seconds. And it does it with 90% less water than a traditional sprinkler system. Nozzles are placed throughout the ship in key areas. Water is pressurized in this tank, then blasted through the nozzles that atomize it. The resulting mist blankets a large area, while pressure forces the fog down to the heart of the blaze. The key to its success is reducing the temperature of the fire and knocking it out as quickly as possible. The system can be activated by temperature gauges, smoke alarms, or manually. There's plenty of other things to keep a crew occupied out here, like other boats. When you're this big, you sure don't want to hit them or knock them over with a big wake. So the hull is designed with wakeless technology. The wide top section floats on a narrow underwater section, perfect for cutting through the water. And even when cruising at 25 knots, it produces almost no wake. Up on the bridge, a state-of-the-art navigation system helps captains counter tides and currents, see through thick fogs, and make sure the ship arrives on time. They also have an autopilot system that's guided by GPS to help locate other ships. And when they're cutting through narrow channels between islands, there's a lot on the line. One wrong move in these busy waters, and the ferry could run aground. So one lucky crew member stands by, ready to drop the machine's giant emergency brake, the anchor. If the engine fails, it's dropped immediately, bringing everything to a quick stop. But what if things do go really wrong and the ship has to be evacuated? Where are all the lifeboats? They're safe, sound, and out of sight. These lifesavers are inflatable. In the unlikely event of an emergency, slides blast out the side of the ship and passengers take a 5-story ride. Massive self-inflating lifeboats wait at the end of the slide. Designed specifically for ferries, it's the fastest evacuation system ever made. And it leaves passengers free to enjoy their crossing and the view from high above the water, while saving a multi-billion-dollar expense of having to build a bridge over 40 kilometers of ocean. Besides, who wants to drive over a static bridge when you can slide onto a moving one that does the work for you? This is an Oshkosh Striker, a custom-built firefighting machine designed to protect airports and passengers around the world. If a plane crashes out here, the Striker's gotta respond in seconds, protect firefighters from jet fuel blazes, and put the fire out fast, even if there isn't a hydrant in sight. Toronto, Canada's Pearson International and its 5 runways are spread out over 18 square kilometers of uneven terrain. It handles over 30 million passengers and almost 500,000 flights every year. It's a great place to see the Striker in action and to get a sense of the challenges this machine has to overcome. Let's see how it works. To fight fires out here, you need superior firepower, extreme mobility, rock-solid stability, and total visibility. Fires fed by jet fuel pack a lot of punch, so you need more than regular lines and hoses to fight them. The Striker comes with joystick-controlled roof and bumper turrets that can attack flames from over 60 meters away. A design feature that is as efficient as it is powerful, thanks to the machine's high-powered water pump and its impeller. Water is sucked into the pump, then it hits the spinning impeller. Enormous water pressure is created by centrifugal force from the spinning action of the curved blades. Design features that allow a single firefighter to control a blaze. And if burning fuel ever threatens the Striker, it has 5 undercarriage nozzles to create a wet safety area on the ground around it. The turrets are fed by an onboard tank that carries 17,000 liters of water, enough to fill about 25 queen-sized waterbeds. And all that extra weight has to be moved fast. Jet fuel fires can rage at over 1,000 degrees Celsius, so they can burn through a fuselage in minutes. So every second counts. To reach crash sites fast, these machines need amazing speed and handling. Easier said than done when you're moving over 50 tons of aluminum and rubber. Speed starts with a 950 horsepower engine that lets the Striker hit 85 kilometers an hour in under 35 seconds. Onboard GPS plots the quickest path to the accident, automatically directing the striker around busy airport roads and runways. That takes care of speed. Now you have to control it. Firefighters are always at risk racing to emergencies, so traction and stability are critical. A fully independent suspension lets individual wheels ride as high as they need to. All-wheel turning helps the operator with precision. The striker can also deflate its tires to increase traction if it has to go off-road. And big clearances mean it won't get hung up on the way. A massive wraparound cab that comes with 80 square feet of glass and total panoramic views ensure drivers never get blindsided. Hand lines also allow firefighters to get out and attack the blaze from different angles. With tools like these, the striker can put out almost anything in record time. And it needs to. When a plane goes down, the passengers and crew have only a few moments to escape. Fortunately, with the Oshkosh striker on the scene, they've got a fighting chance. If you've ever dreamt about digging to the center of the Earth, you'll want to meet the Red Boar 100, the biggest and baddest drill in the world. Light assault vehicles are essential to modern infantries. The Lav 3 ranks with the best of them. Recycling machines work together to take care of all that stuff we toss into the box, no matter what it's made of. Stirling engines have been around for 200 years, quietly waiting to change the way we power pretty much everything. Let's take a look inside these machines and see how they work. This is the Red Boar 100, one of the most powerful drills on the planet. For blasting tight spaces like mines, city sewers, and subways, this type of drilling is faster, cheaper, and cleaner than the old-style drill and blast. It cuts an 8-meter wide hole, hundreds of meters deep, through solid rock. Big enough to swallow trucks. Lots of trucks. They call the 100 a raise bore drill. Here's why. This machine drills up, raising its cutter toward the surface. Its massive cutting tools called a reamer, driven by hydraulic cylinders that crank out 1,000,000 kilograms of thrust. The same force blasting from NASA's latest rockets. As mines expand, they need extra vent shafts for workers and access tunnels for heavy gear. Here in northern Quebec, the Queen Louise is drilling a new ventilation shaft at a gold mine. Let's see how it works. First, the reamer is positioned in the target zone of an existing shaft, ready to be attached to the drill pipe. The machine up top has to punch a pilot hole through almost a kilometer of rock to hook up with the reamer below. A lot easier said than done. Here's the problem. Think how much effort it takes you to push a small drill through a piece of wood. Now, imagine the strength required to drill through almost a kilometer of solid rock. First, drilling the pilot hole through rock this hard can easily deflect the cutter and force the drill pipe way off target. And second, Pulling the reamer up through so much rock has to be done right. So this part of the operation needs both strength and precision. Electric motors power hydraulic cylinders that generate enough thrust and torque to keep the pilot drill turning. As the bit descends, 2-meter drill sections are added piece by piece, pushing it down further. Each of the sections feature a unique thread design to deal with the machine's powerful torque and thrust. The threads work with the torque to lock the sections together. This is critical in helping the drill stay straight. If the drill is deflected even by a small amount, it can result in the drill missing its target. Small mistakes, when amplified over hundreds of meters, become big ones. So all the machine's power needs some precise management. If it deviates more than 1%, that's 10 meters for every 1,000 it goes down. Pulling back up becomes a real problem. So if the drill starts to go off course, the operator uses the machine's steering function to get it back online. They don't let rookies drive this thing. Once the pilot hole is complete, they're ready to hook up the big guy, the reamer. With hundreds of jagged titanium teeth, strong enough to tear through rock. But pulling the reamer up through such a long distance has to be done right. Mistakes down here cost a lot of time and money. On a good day, this machine cuts through over a meter of rock in an hour. So, if all goes well, this hole will take about 6 months to finish. Much faster than traditional methods. In order to produce the force it needs to pull, a raise bore drill uses the earth below it for leverage. This innovation allows the red bore to generate over 1.7 million kilograms of pulling power. All the falling rock crashes to the mine floor and is removed by loaders and trucked out through tunnels. The machine is so automated, you only need a couple of operators up top and an observer down here keeping an eye on things. If something goes wrong, he gets on the horn pronto. Back up top, whether adding sections of drill pipe going down or removing them coming up, you need a hand. In this case, a powerful robot wrangles each 1,200 kilogram section. On a hole this deep, that adds up to over 500,000 kilograms of steel. The final challenge is ground control. Precision drilling the main hole up is as vital as it was drilling the pilot hole down. When you're cutting an 8-meter hole, you have to make sure it's going to stay 8 meters. Any wider, it'll crumble, needing very expensive support work. So drillers have to know what kind of rock they're dealing with and be able to react quickly to underground surprises. The Red Bore 100 weighs in at about 75,000 kilograms. And falling down the same hole it's digging would be very bad. So this machine starts every job with structure and support. That comes in the form of a poured concrete foundation and steel girders that span the area over the projected opening. It'll take the Queen Louise another few months to finish up here. When completed, the hole is secured and handed over to the mine. And she moves on to her next job. Depth, power, and precision. When you call yourself the most powerful drill in the world, you better deliver. And the Red Bore 100 sure does. This is the Lav 3. A light assault vehicle used by modern mechanized infantries. It's called light because it weighs less than a tank. But it's plenty tough and can handle the assault part too. At this Canadian Forces base in Petawawa, Ontario, the men and women of the 2nd Mechanized Combat Brigade are training for a tour of duty in Afghanistan. The conditions may not be identical between the two countries, but the challenges for the machine are the same. Move across rugged terrain without breaking down, find and destroy threats in the hills, and work as a team with the soldiers it carries. Armies around the world rely on this machine because of the way they protect and deliver troops. Let's see how it works. The LAV-3 is a miniature army base on wheels. It comes equipped with tires and a suspension system that lets it climb pretty much whatever it wants. And an engine that can top 100 kilometers an hour. Not bad for a machine that weighs 5 tons more than a school bus. These mechanical details make sure troops arrive fast, safe, and ready to fight. Whether hunting or fighting the enemy, gathering information, or rebuilding vital infrastructure, there's no substitute for feet on the ground. And delivering those feet is what this machine is all about. The start of every mission begins with a load-in. Supplies are carefully laid out for pickup, especially these, rounds for its primary gun, the Bushmaster M242. Weapons, ammunition, rations, water, and other equipment crammed into every available nook and cranny of the hole, the compartment where the soldiers ride. Once they leave base, troops are on their own, so they can't leave anything behind, including their most important cargo, themselves. The carrier hold of the LAV-3 takes up to 7 personnel, and it's a tight fit. Add to that the machine's crew of 3, commander, driver, and gunner. Carrying that number of troops is a big advantage. Smaller vehicles may be fast and cheap, but they carry fewer personnel, and they don't offer nearly as much protection. The LAV's thick outer skin is designed to stand up to .50 caliber fire and more. Fully armored, the LAV weighs in at a hefty 17 tons. Its large fuel tanks allow it to travel almost 500 kilometers without needing to refuel. And it can maneuver well in tight spaces. Critical for working in urban environments and for getting the job done no matter what surface it's on. The tires are positioned close together to mimic tank tracks. This allows the LAV to cross a 2-meter wide trench. And onboard compressors can deflate the tires for slick terrain where extra surface area is needed. Fully independent suspension keeps the ride rolling. But tough terrain isn't the real threat. What's on it or under it is. These days, that means improvised explosive devices and car bombs. If there's suspicious activity on the road, 2 hatches allow troops to keep an eye on anything sneaking up from behind. The rest of the crew keeps focused on what's ahead of them. With crack soldiers on board, it's easy to stop, establish a perimeter, and check out potential trouble. And if you're heading into sniper country, batten down the hatches. From inside, drivers and gunners use advanced periscopes to get clear views without exposing themselves to enemy fire. Driving the machine is pretty much like handling any heavy-duty vehicle. It comes with a big steering wheel, gas pedal, brake, and gear shift. Here's where the similarities end. The Bushmaster M242 autocannon, a weapon that's as reliable as it is powerful. Most machine guns use a shell's explosive recoil to eject empty casings and load the next round. But in guns powered by explosions, a lot can go wrong. Heat is a problem, and so's jamming. If a casing gets stuck and the next bullet can't load, you're no longer in the fight. This is not an option for the Bushmaster. So on this gun, rounds are loaded and ejected with a chain drive that's powered by a small motor. Even if a shell gets jammed, the chain just pushes it out. It's the action of the chain that drives the bolt back and forth. The shape of its barrel helps the M242 overcome another automatic weapon challenge, overheating. It's fluted, and this helps by exposing more surface area to the cooling air. The gun spits out massive shells at more than 3 times the speed of sound and has an effective range of 2 kilometers. With all this power and mobility, light assault vehicles have become a vital part of modern infantry strategy. LAVs normally conduct offensive operations as part of a combat team. The machine's high mobility and toughness make it ideally suited to support unit movements. Once troops hit the ground, the LAV turns into a mobile command center, at the ready to provide backup in any way it can. One thing the LAV-3 does not do a lot of is retreat. When combatants see a line of these guys rolling in, their usual response is to turn and head for the hills. Speed, handling, heavy armor, big guns, and a belly full of soldiers makes this a machine to be respected. A typical Canadian uses 4 trees worth of paper annually. Americans toss enough aluminum cans away every month to rebuild its entire commercial air fleet. And in 1 year, Europe goes through about 10 million tons of newsprint. Recycling just 1 ton of newspaper saves 19 trees, 3 cubic meters of landfill, and 29,000 liters of water. Good thing we're becoming better recyclers. Every year, more and more materials are collected worldwide to be sorted and transformed into something new. And the single-stream recycling machine helps make that possible. It handles paper, glass, metal, cardboard, and plastic. Let's see how it works. Step 1. The material arrives. A front-end loader pushes everything onto a conveyor belt. There's a lot of it, and it's mixed up with tons of garbage that has to be manually removed before the recycling materials can enter the machine. Now, all this stuff has got to be sorted. No small task. Fortunately, this machine is a master sorter. The challenges in here are always the same. Find and get rid of the bad stuff, and then sort the good stuff into different piles. It comes armed with 3 sorting screens for cardboard, newsprint, and magazines, as well as a set of magnets to handle metal. First up, the cardboard screen. It's made of rotating steel discs. As the discs spin, their spikes knock pieces of cardboard into the air and onto a conveyor. The cardboard flows onto a bundling area. It's on its way to becoming new packaging, like egg cartons. The rest of the material moves on to stage 2. The plastic, metal, glass, and paper arrive at the second sorting screen. This is the newspaper one. It sorts different grades of the material using these rubber discs. After being separated, it's sent to paper mills to make more newsprint or toilet tissue. Glass, metal, and plastic roll off the screen and move on. Magazines and other materials like flyers fall to the same conveyor. They're made from different fibers than newspapers and need their own sorting. And that happens at the final screen. The heavier paper sticks to these rubber discs with the help of fans. This type of paper is recycled into products like gift boxes, game boards, and greeting cards. That's it for the screens. Now it's time for the magnets. The machine has to separate metal into 2 groups, ferrous and non-ferrous. Ferrous metals, like steel, are magnetic. Non-ferrous metals like aluminum, copper, and tin are not. So to start with, a big magnet is used to take out the ferrous materials. Then, the machine targets aluminum, an extremely valuable recycling material. You can make 20 cans from recycled aluminum with the same energy it takes to make 1 can out of new material. Tossing out just one is the same as spilling half a can of gasoline onto the ground. To separate aluminum, the machine needs help from the electrical phenomenon called an eddy current. The aluminum picks up a charge as it passes over this magnet. They now both have the same charge, so they repel each other. Same as when you try to push two magnets together. Once separated, the aluminum is bundled, then shipped to be melted down and repurposed. Finally, the plastic and glass are separated by hand before further processing. The machine ensures that about 95% of what it started off with gets recycled. The basic materials of paper, plastic, and metal are repurposed into everything, from carpets and ski jackets to beer cans, takeout containers, and home insulation. And that's good news for everyone. You're looking at a Stirling engine. This model, first used as a water pump, has been working for over 100 years without a hitch. It's among the most efficient engines ever invented. First built in the 19th century, the full potential of the Stirling is finally being realized. It can convert almost any source of heat into energy cleanly and quietly. Anywhere you need electricity and heat, the Stirling engine may be what you're looking for. And new versions of this machine may soon be powering our homes. Let's see how it works. A basic Stirling engine needs a heat source, a cooling source, and a piston. That's about it. When you heat a gas with fuel, it expands and pushes a piston. Cool a gas with, say, water or air, it contracts and pulls the piston. And if you're using waste heat, there's no direct combustion or emissions. It's also very quiet. This model is a 2-piston version. The first piston drives the engine, and the second is harnessed to power a water pump. All it needs to work is heat from the wood stove. In theory, you could use a Stirling to create power from anything that produces a constant source of heat, like the inside of your computer. Designers are working on a small Stirling to power the CPU fan with waste heat, and automakers have tinkered with Stirling engine cars since the 70s. So if the Stirling engine is so amazing, why isn't it powering everything? Because it has a number of challenging disadvantages. The main ones are they're expensive to build, and the older versions don't produce much power for their size. Another one is that they take time to warm up and start their engines. Who wants to wait 20 minutes for their car to start? But for home applications, there is change afoot. Rather than pump up and down, it uses heat from a gas flame to move these 4 pistons that are connected to a very special gear called a wobble. This converts Stirling power from up and down into round and round. And it spins a small generator that pumps out electricity directly to your house. This mini power plant is being rolled out in central England. It's called a Whispergen. It's fed by gas and connects to a home's central heating supply. But as it's heating the water for your shower or the radiators for warmth, it's also producing electricity. Inside each machine, there's a generator that's wired into the home's electrical system. If you're using electricity while your Whispergen is on, it will help power your lighting, TV, and other electrical appliances. About the size of a dishwasher, this machine is very efficient. It converts about 90% of the fuel it gets into usable energy. A lot of the electricity we get over the grid comes from power plants that are less than half that efficient. So these things save big on bills and emissions. It won't be long before Stirling engines are popping up in all sorts of places. solar plants, jet engines, you name it. Pretty cool for a machine that's 200 years old and virtually anonymous.